a great presentation.
Thank you, Nobu. I would like to thank you for inviting me to be part of this panel, and also for choosing a topic which I think is of critical importance for our community and for the whole society as such. What can thermal science do today in order to satisfy the needs of the society? There are many important questions, and I have picked up only one particular example, which is to obtain sustainable and safe energy supply with the least environmental impact. I've chosen this, but I'll try to make my points as we go through as to where we stand, what we can do, and how we should approach it. There are three aspects to this problem. The first one is energy, which of course we're very familiar. Generation and conversion, thermal sciences has been extensively involved, distribution, to much lesser extent, storage to some extent, and utilization, including manufacturing and many others to some extent. The environment and safety and security are two aspects which are equally critical, equally important, and we have not really been involved with it too much, despite the fact that environment is very much a thermal science problem. We hear about global warming, we hear about radiation, we talk about greenhouse effects, but when you look at the papers, most of the papers are not being written by thermal scientists. So we have been kind of out of the loop, and that is something that I feel very strongly, that not only do we need to do interdisciplinary research and work with many of our colleagues, we do need to take leadership in many different areas. Without that, we will not make an impact as a society, as a whole unit. We will make a society impact. Environment, I put down a few things here, which is exactly what I'm talking about, and safety and security. Again, I'll talk about it a little bit later as we go along, but we are in a very fortunate condition because we deal with thermal energy, thermal systems. Just look at where this goes, from manufacturing, energy systems, cooling systems, environmental safety systems, aerospace. You don't have too many aerospace systems without thermal sciences. Transportation, whether it's an automobile or a train, air conditioning systems, heat transfer equipment. So we are essentially almost in every domain of what the society needs or what the society uses. But still, when you look at an overall impact from the society on issues which are of critical importance to the world, we don't seem to have the standing that we should have. And therefore, I think this question is very, very important. How can we meet this challenge? What should we be doing in order to make a major effect? Energy, certainly there are important considerations. I've put down a few of them here. The fossil fuels, of course, have been the classical domain, but the renewables, we have gone into them, but probably not to the extent that we should, and we still have many areas, particularly in storage, even in solar, even in photovoltaics, as we well know, we do manufacturing. So we can talk about making solar cells much cheaper. Solar cells so that become a possibility for many people in the world. Environment, unfortunately, is one of the cases which I feel we have been sidelined. We have not worked on, we did a lot of work in local pollution. If I go back to the 1970s, we were doing a lot of work on local pollution. But then we kind of stepped back, and all the issues of climate change, I was looking at papers. There are thousands of papers coming out each year. The actual number of papers coming out thermal science is very, very small. But if you talk about how this energy imbalance comes about, what the greenhouse effect is, it's basically thermal sciences. Safety and security, again, a very major issue. I'm not talking just about politics and other terrorism activities and so on. I'm talking about fires, explosions, and many of those have come up and have driven our research. But should we be involved more? Can we spearhead these issues? And I mentioned here standalone systems. That's a very important idea, that we can make systems which take you away from the grid and you're able to provide energy to remote areas. For instance, in India and many other countries where you can provide energy to the local people and change the conditions completely. We do have three different needs. We have developed nations which may worry about environment in case they don't worry about it, and safety. Then you have developing countries which worry about cost and supply and pollution, and the underdeveloped countries which basically just want the standard of living to go up and they want to get the energy coming in. So the challenges are many. I put a whole list up there, and many of these slides will be uploaded later on, but certainly you can see that in renewable sources, for instance, the processing of materials is something that we can actually take leadership role in. Energy storage, certainly we did some, but again, we need to take a leadership. Some of those, like recovery of waste heat, is important. Optimization, it's amazing how much we can do with optimization. We have not gone into it as much as we should. And then, of course, some of the others that I mentioned, climate change, greenhouse effect, sustainability, security, and so on. So all those are challenges that we face. Where do we need the work? Certainly in energy storage. We certainly need in the efficiency, reduction in consumption, optimization, efficiency. I showed a number of systems that we have we really gone as far as to reduce the consumption, make them more efficient, and in many cases we have not. And material processing, and again, climate change, environment, and so on. Let me take a couple of examples, just to illustrate that. This is a very straightforward problem for a thermal scientist. This is a power plant rejecting energy into a lake, into a pond, through a cooling tower or without a cooling tower. What you see there is this temperature cycle of a lake. The lake may be in USA, the lake may be in Russia or any other country, but typically it's isothermal in the winter, and it is typically stratified in the summer. So it's isothermal in the winter, and it's stratified in the summer. The temperature difference is there. This is the temperature cycle. Now, as thermal scientists, we can do a fantastic job modeling it. We get a good result of modeling, we can show what is happening. We can put power plants on it, and we can show that the effect of the power plants would be to have temperature rise and the cycle changing. Now, if we stop here, our impact is basically going to go into journals and papers and books. It does not have the impact on the society. Let's go one step further. Suppose we do go and look at what kind of imbalances are occurring, and we start working with people who do the biological systems. We start talking about the oxygen content. We start talking about the effect on the bioorganisms and so on. And the temperature difference is very small. Can we tell people and guide them that the temperature differences we're talking about are very small, but even these 2-3 degree temperature differences would destroy the lake. In about 10-15 years, it would be a dead lake because of the effect on the bioorganisms. So that's where you do need the interdisciplinarity. But you have to get into the system. You cannot just say, okay, let's collaborate with a biological person. You need to get into the system. You need to own it, and leadership has to come from the thermal sciences so that you can ultimately make a big impact on it. Let me take another example. Data centers, very common. Data centers use a very large amount of energy. Again, as mechanical engineers, thermal scientists, we can do a nice modeling. We have nice software. We can show exactly what the temperature levels are and so on. If we do this, we are a supporting role. We are helping people who design the data centers and so on. We are not doing the leadership work. But let's go a couple of steps further. What happens if we start talking about the locations where these data centers are positioned? If we start talking about the environmental conditions there, how can we change the energy that these data centers are using? Now you're talking about different loads. How do you distribute the loads? And ultimately, you will end up much, much lower energy consumption. So we have gone one step further, but now you're linking with computer scientists, you're linking with distribution people, you're linking with electrical energy people, and so on. But that's where you start making an impact. Accidents and fires. This is the picture of a fire in a power plant. These are some fires in buildings. We have done a lot of work on fires over the years, and these are modeling at the bottom that I'm showing. Work has been done on fires, but in most cases, these have been driven by fire that occurred. 9/11 is an example. The moment 9/11 attacks occurred, the thermal science community did not react immediately. It took a very long time for the thermal science community to react. As a consequence, most of the work went to the civil engineers, the architects, and many other people before it came to the thermal science, even though the basic collapse was fundamentally driven by thermal sciences. So we did not take the ownership and did not take the leadership, and we did not have the interdisciplinarity which is needed. So coming to funding and control, the federal government would form the policies and regulations, and that's where the top-down or bottom-up we are talking about. But we really should be in a position to make changes in this policy. We should be able to guide some of these policies. Jack Kennedy many, many years ago said, okay, we want to go space. But if you look and follow through the next 30, 40 years, there was a fair amount of interaction between the scientists and the engineers and the overall policy. So it's a question of how do you modify the policy so you can do your own work while that effect continues. Industry, of course, is very targeted, but again, in fact, I worked initially with Bell Labs, which basically said that work in the area of communication, but do whatever you want, but it must, in the long run, apply to communication. And the research that came out of Bell Labs was fantastic. So you need the boundaries. If they are flexible, you can work very nicely with them. If they are rigid, like from an industry, it becomes more difficult. Academia obviously wants to do long-run research. How do we align it with the policy? Can we modify the policy, and so on? Research direction is critical. We have to justify it. We do like to do the fundamentals and try to understand that. But at the same time, we need to show how in the long run it'll make an effect. And in most of the problems that we are encountering today are not going to be pure heat transfer, pure fluid mechanics. They would involve other areas. We have to get into those areas, get the information, and ultimately take leadership role. And that's what I'm focusing on, that we do need to guide the future policies with respect to various energy sources, in terms of why this is important, how do we link our research to applications that are there, and critically having a leading role, we need to articulate our research, how those research would affect the areas of great need, and ultimately help formulate the policy. So some of these examples I've taken, that's what I'm trying to indicate, that thermal scientists do have a role to play, a very major role. In many, many cases, we have been a supportive player rather than a leader. We do need to link with other areas and then take a leadership role while keeping the long-distance focus on the research needs, on the societal needs that we have. Thank you very much.